although they're going to be a little bit of a pain since they're word problems and all. Okay. So in all of these problems, and actually this will be the case with problems in the next lesson too, the problems will be about applications in which the goal is to maximize or minimize something. For example, the problems in this lesson deal with either maximizing revenue or minimizing costs. So the idea, so the challenge of these kind of problems is first coming up with the function that you're trying to find a max or min of, and then going through the same procedure as in previous lessons, where you take the derivative, set it equal to 0, find critical points, and so on. So 2 or 3 problems are about inventory control, so trying to minimize inventory costs. So we look at the relevant facts here. So this store expects to sell 110 flat irons during the year, and here's the cost to store one item for 1 year. And then so the idea is the store will order a certain number of irons, and then over time it will sell them. And then once there aren't any more, it has to go and order more. So every time they place an order, there's this fixed cost. So $8.25 every time they order. So the goal is to find out how many times a year do they need to order, and then when they order, how many irons should be in each order to keep inventory costs at a minimum. Because there's competing concerns here that if you go to extremes, like let's suppose you are going to order only one time at the beginning of a year, you're going to go ahead and order 110 flat irons, and then that's your only order for that year. So that helps in the sense that you're only shelling out this fixed cost of $8.25 one time. But now you have 110 flat irons to store at $3.75 a pop. So that will increase the inventory costs. If you go to the other extreme, let's suppose you are only going to order one flat iron at a time, and once you sell it, then you order another one. So then you're going to be placing 110 orders per year. So you're paying next to nothing for storage because you're only going to have at most one flat iron in storage at a time. But you're shelling this cost out times, 110 times during the year. So the idea is to find a balance between these two extremes that will lead to the minimum overall cost of ordering and cost of storage together. So for something like this, where we know how to find a minimum of a given function, the trouble is we're not given the function yet, so we have to come up with it. So we need some variables to describe various quantities, unknown quantities that we have. So X will be the number of orders that are placed each year, and then N will be the lot size, or how many irons are in each order. So all we know about these two so far is that the number of orders times the lot size is has to equal 110. But there are many combinations that could give you 110. It could be 2 orders of 55 irons each, or it could be 5 orders of 22 irons each. It's going to be something like that. So if we can find one of these variables, X or N, then we can take 110 over that to get the other one. All right, so now we're going to use these variables to express the total inventory related cost. And so that's 2 parts: cost of ordering, cost of storage. And I mentioned this already. This is the relationship between x and n. So, okay. So whatever x is, n will be 110 divided by x. So that'll help us at the very end. All right. Now, so one thing that's not really mentioned in the problem, but I need to emphasize here, is that there is an assumption about item storage. That however many items you order, the assumption is that once you have these items in stock, they're going to be sold over time at a uniform rate. Um, so let's suppose you order 20 irons. So once you come in, you're storing 20 of them, but then you sell them over time, and so the number that you're storing goes down. Therefore, your storage cost is going down until eventually you have none, and then there's no storage cost. So to simplify matters, we assume that however many items you order at a time, so n, you're storing half that many at any given time because that's the average. Sometimes you're storing a lot, sometimes you're storing none. So we just split the difference and say we're assuming we're storing half the number of items you order, because on average that's how many are in stock. So that will help us come up with our function for describing the overall cost. So here's our cost function in terms of these quantities that we don't yet know. Every time you order X number of orders, then you're paying $8.25. So that's that part right here. So that's the ordering cost. Here is the storage cost. If n is the number of items you order at a time, on average, you have that many in storage, and it costs $3.75 to store each one. So this gives you these two. The sum of these two is your inventory cost. So this is what we want to find the minimum of. This is sort of the main part of a problem, and really this is a part that's new. So any questions about how this function was obtained? Now, we only know how to find a max or min of a function of one variable. The trouble is this function has two variables, x and n. But that's okay. We know how to deal with n because we know that n is equal to 110 over x. So we can fill that in. So I've just replaced n with 110 over x. And now all of this can be simplified. So we just multiply the numbers together, and this is our function. So now, in terms of the number of orders, this is our inventory cost. So we're going to find a minimum of this function of x, and then we'll know how many orders we'll place. Then we'll just take 110 over that. That'll tell us the size of each order. So now we can do, as we've done in previous lessons, for finding a minimum, we need a critical point. All right, so there's our function, and now we go ahead and take the derivative. Actually, I'm going to rewrite this as 2 of 6.25 x to the minus 1, because it's 1 over x, but that's the same as x to the minus 1. That's better for taking a derivative using the power rule. So we get 825 from the coefficient rule, and then we have minus this number times x to the minus 2, because we deduct 1 from the exponent. But x to the minus 2 is the same as 1 over x squared. So that is the derivative. We need to set the derivative equal to 0 and solve. All right, so now we go ahead and fill in a derivative, set it equal to 0. and then oh, that should be. Oh, okay. There's a fraction command missing here. Okay, that's what we have here. And then I'm going to multiply both sides by x squared. To move it over here. And then if we divide both sides by 8.25, that happens to work out nicely, as your calculator will tell you. And we get 25. Of course, we're only interested in the positive square root because obviously we're not going to place a negative number of orders. So this is our one and only critical point of relevance, and that is x is equal to 5. So what this says is we are placing 5 orders per year. So we have that part. So then we just substitute that in here. So take 110 over that, and that will give us the number of items we'll order at one time. So we just fill in x equals 5 there, and that works out nicely to 22. For these problems, because we're dealing with ordering items, you can't order a fraction of an item. The numbers are supposed to work out nicely, so if they don't, that is a sure sign that something went wrong. So that's it for this problem. 5 orders per year, 22 flat irons per order, for a grand total of 110. And this happens to be the combination of many choices that minimizes the inventory cost. Questions about how that was done? All right. Now that was a problem about minimizing. Here, this is about maximizing. So the actual calculus part of this will be the same, but now we have a challenge of coming up with a different sort of function. So here we have a jewelry store. So when it sells on average 56 diamond bracelets, $700 each. So the idea is we want to consider raising the price in the hope to get more revenue. But what they estimate is that if you increase the price by $70, then you're only going to sell 54 bracelets. If they jack it up another $70, then they'll sell 52 bracelets and so forth. So we have an idea of a relationship between increasing the price and selling fewer bracelets. So we want to get an idea of what they can get away with. What is the best combination? Because on one hand, they're getting more money by raising a price, but they're also getting less money from selling fewer bracelets. What is the best combination? So like in the previous problem, we need a function that takes all of this into account to figure out the ideal balance between these things. So we need a function that will describe the revenue. So the idea is we need a variable, and a convenient variable here that we'll call x is how many price increases are made. So we're going to assume that the price is increased in $70 increments because there's a clear relationship between increase in price and selling fewer bracelets. So we're going to express the revenue as a function of the number of price increases. So what would that be? All right, so revenue we're going to call R of X. So what we have here, this part is the price. So $700 at the starting point, plus 70 times the number of price hikes that have been made. So, so in terms of the number of price hikes, that's the price. Times how many are sold. So every time the price is hiked by $70, that's 2 fewer bracelets. So that's why we have a coefficient of 2 here. And we're selling fewer bracelets, so that's why it's negative. So here we have, because revenue, of course, is going to be price times number of units sold. And here we've described both in terms of how many price hikes are made. So then what you could do is multiply all that out. So if you're foiling it, then this is a function that you get. So then you follow the same procedure as before. We take a derivative and set equals 0. And in this case, it's just going to be using the power rule. Oh, these terms were combined, by the way, since they both have a coefficient times x. So that's the combined term. So now we go ahead and take a derivative. So this gives us 0. Here we have a coefficient rule that gives us this. And then we have the 2 coming down times 140 gives us minus 280 times x. So now we can set this equal to 0. And then just carry out the algebra from there. So move the 280x to the other side. Okay. Actually, that step wasn't necessary. Now we can just divide both sides by 280. And so it turns out that raising the price 9 times gives the maximum possible revenue. So now what we can do, if we go back to what the problem is asking for, find the price per bracelet that will maximize revenue. So now what we can do is take this number of price hikes and substitute that into the formula that we already had for the price. So the original 700 plus $70 per price hike. So we just substitute 9 price hikes in here and work that out, and we get 1330 is the ideal combination. So even though you're not selling many bracelets, well, actually, even though a problem doesn't ask for it, if you take the number of price hikes and figure out how many were sold, so that'd be 56 minus 2 times 9. So you end up selling only 38 bracelets, but you're selling them for $1,330 a piece. So that and turns out to be more revenue. Actually, I'm going to give you an idea of the difference it makes. I'm going to work that out for you. So if you sell 70 bracelets, 56 each, what you get is $39,200. And then revenue from oh, sorry, that's 56, not 70. And sorry, I have numbers backwards. Okay, so 56 bracelets, 700 each. The original amount sold, the original price. Yeah, 39,200. Okay, now the combination that's supposed to maximize revenue is 38 bracelets, $1,330 each. That's $50,540. So that would mean 28, actually 29. 29% more revenue than this combination. So even though you're not selling as many, you're still making substantially more money. So it's worth the effort to try to figure out what the best combination would be. Now, it's just based on an estimate that they think, okay, we hike the price by this much, we're going to sell 2 less. That may turn out not to be true in practice, but if you look at your like historical sales, that can give you an idea. The best idea you can hope to get anyway as to how things will change as you change the price. Excuse me. So questions about uh, this one. Okay. Sorry, it doesn't mean that's how this zooms in, so I can't really see what I'm typing. Oh, dang it. Okay. All right. So here we have one more inventory control problem. Dang it. Okay. So we have, like before, this is how many you expect to sell, 400 items. And then here's a storage cost, also same as before. The one little wrinkle is when you're ordering, the previous problem with flat irons had a fixed cost per order, but there's also a per item cost to consider. So that's going to be an extra term involved in the total inventory cost. The question is the same. So what's the lot size? How many times per year do you order? Again, to minimize inventory costs. So like before, X is the number of orders per year. So then the bracelets per order is 400 divided by X. So the grand total will always be 400. So now we need to describe the inventory cost. So this is the cost of really storage. Yeah, I should change that. Okay. So the cost of storage is how many items per order divided by 2, because we assume that there's half in storage at any one time, times the cost to store them, which is $1.40. But now we want to express this in terms of X, because that's the number of orders per year. That's the variable we're really going with. So then we fill in what N is in terms of X, and then work all that out, and this is what we get. 280 divided by X is the cost of storage in terms of the number of orders. So what that means is the more orders you place, the less your storage cost will be, which makes sense because you're storing fewer items at a time. But there's the other part of inventory cost to consider, and that is the cost of reordering, which will increase with X. Okay, so here we have $17.50 is a fixed cost of ordering. And then we have $4.20 times the number of items you order. So then we again fill in N equal 400 over X and work all that out. But this is the cost per order. So now we have to put everything together. All right, so here we have a storage cost. Here's the reorder cost up here. That's just for one order. we have to multiply that by the number of orders. So as I said, this part of a cost will actually increase with x. So now this is a function that we want to find a minimum of. So now we have to do some distributing here. And then we'll find the derivative. So here's the function simplified. So we distribute the x through here and get this. So what we see here is, as the number of order increases, as the number of orders per year increases, this part of a cost goes down. This part of a cost goes up. That's why we're doing this, to find the ideal combination, because it's not obvious. So now we go ahead and take a derivative. And it's helpful to keep in mind, we have 1 over x. The derivative of that is minus 1 over x squared. So you don't absolutely have to rewrite it as x to the minus 1. I just do that to show you where the derivative comes from. But if you just keep in mind, 1 over x, the derivative is minus 1 over x squared. In fact, I might save you a little bit of time. And then taking the rest of the derivative here, this is what we need to set equal to 0. And then solve for x to get the number of orders. So then if I move this to the other side, and then multiply both sides by, we'll just negate both sides, multiply both sides by x squared, and then divide both sides by 17, 5. Oh, something's wrong here. Oh, something was mistyped. 280 divided by 17.5 is 16. Oh, wait. Okay. Like I said earlier, these problems, the numbers are supposed to work out nicely. You're not going to place the square root of 280 orders. And we only care about the positive square root, obviously. So x is 4. So the number of orders per year is 4. So that is our minimizer. So now we find out the number of items in each order. So we take 400 divided by x. So we get 100. So the optimal combination of minimizing storage costs is that we place 4 orders per year, 100 bracelets per order. So it's going to be 400 no matter what, but at least this way you're not spending as much on ordering and storage as you would with other combinations. Any questions on that one? All right, so for the inventory problems, keep this in mind because it's not stated in the problem. It is stated in the learn section, but I'm guessing not too many of you look at that. That's the assumption here is however many items are in an order, the cost of to compute the storage cost, we're assuming that half that number of items is in storage at any one time. So then you multiply that by whatever the storage cost is per item to get that part of the cost. And for ordering costs, some problems, as we've seen, have just the fixed cost, and others have other problems that have an additional per item cost that's figured in here, the $4.20 per item ordered. So that significantly affects things. Does anyone have any questions on the problems from this lesson? Okay, I will stop recording at this point, and unless you have individual questions, you are free to scram.